The research suggests that nanobots could assist medical professionals in complex tasks after passing through tiny spaces in the human body. One of the biggest potential applications is for extremely targeted drug delivery to specific cells within the body. As we'll soon see, this has already been achieved. Scientists also believe that nanobots could be used to reduce plaque in veins, solve dietary issues, along with a whole slew of other medical uses. They'll be able to operate in parts of the body where the blood flow is slower, such as capillaries in the eye or fluids outside the circulatory system, such as ventricles of the brain or urinary tract. So all of you have probably heard of CRISPR gene editing. Although not directly related, CRISPR is an offshoot of the nanobot idea. CRISPR is actually an exploitation of a natural molecular DNA function. Scientists use a virus's natural ability to cut and splice the DNA we want to edit at will. We've talked about CRISPR DNA editing in the case of destroying cancer in a previous video. The origin of nanobots is commonly attributed to Richard Feynman, a scientist in the Manhattan Project, the man behind the theory of quantum computers, and a pivotal mind in quantum physics. Feynman solidified his idea in his 1959 writing, "There's Plenty of Room at the Bottom." In it, Richard Feynman imagined a day where machines could be miniaturized and huge amounts of information could be encoded in minuscule spaces, paving the way for disruptive technological developments. The technology would be so good that it could, quote, swallow the surgeon, as he put it. So what is nano? Nanotechnology is the science, engineering, and technology conducted at the nanoscale, which is about 1 to 100 nanometers. Let's put that into a perspective. The ratio of the Earth to a marble is roughly the same ratio as a meter to a nanometer. A nanometer is 1,000,000 times smaller than the length of an ant. A strand of DNA is 2.5 nanometers in diameter, making them the perfect candidate for a basis for nanorobots. There's a couple of types of nanobots in existence today, but right now we'll focus on those made from DNA and those that are man-made. So let's take a look at the state of the art. Researchers at the University of San Diego developed nanorobots capable of cleaning toxins from blood generated by harmful bacteria. These nanorobots are about 25 times smaller than the width of a human hair and are made from a combination of natural red blood cell and platelet membranes and artificial gold wire. They can be controlled by ultrasound, which eliminates the need for a battery during propulsion. While still experimental, early tests have proved successful, with nanobot-treated blood containing 3 times less toxins and bacteria than untreated blood. The scientists note that, quote, this is a proof-of-concept platform for diverse therapeutic and biodetoxification applications, end quote.
By using this natural biomaterial membrane, coating our microrobot, we can impart new functionality, new capability like removal of pathogen and toxin from the body.
Researchers at the Arizona State University and the National Center for Nanoscience and Technology of the Chinese Academy of Scientists injected nanobots made from a folded sheet of DNA into the bloodstream of mice. To perform their study, first, scientists induced aggressive tumor growth in the mice. Once the tumor was growing, the nanobots were deployed to come to the rescue. Each nanobot is made from a flat, rectangular DNA sheet 90 nanometers by 60 nanometers in size. A key blood clotting enzyme called thrombin is attached to the surface. Thrombin can block tumor blood flow by clotting the blood vessels that feed tumor growth, essentially leading to the tumor's death. First, an average of 4 thrombin molecules were attached to the flat DNA scaffold. Next, the flat sheet was folded in on itself like a sheet of paper into a circle to make a hollow tube. These were then injected via IV into a mouse. The nanobots then traveled through the bloodstream, homing in on the tumors. The key to programming a nanobot that only attacks a cancer cell was to include a special homing device that specifically targets a protein that is made in large amounts on the surface of tumor cells. The thing is, this protein is not found on the surface of healthy cells. The result is a DNA device that seeks out tumor blood vessels and is programmed to release its blood clotting cargo right into the heart of the tumor, killing it. The nanobots worked quickly, congregating in large amounts to surround the tumor just hours after injection. According to the scientists, this technology is a strategy that can be used for many types of cancer, since all solid tumor-feeding blood vessels are essentially the same. So here were the results. 3 out of the 8 mice receiving the nanobot therapy showed complete regression of the tumours. The median survival time more than doubled, extending from 20.5 days to 45 days. Healthy tissue was left untouched, and I think this is pretty good for such an early trial. They also tried their system with lung cancer. The tumour tissue showed shrinkage after 2 weeks of treatment. Professor Hao Yan, one of the lead researchers, weighs in with his thoughts. I think we're much closer to real, practical medical applications of this technology. Combinations of different rationally designed nanorobots carrying various agents may help to accomplish the ultimate goal of cancer research, the eradication of solid tumours." End quote. Yan and his collaborators are now actively pursuing clinical partners to further develop this technology. A nanobot device is roughly the size of a red blood cell or smaller. This is too small to add elements like a motor, computer chip, or camera, so bioengineered bots made from DNA are a common platform for such medical tasks. But as you'll see next, nanobots made from man-made materials are possible and are currently being used in research right now.
My name is Tejal Desai. I'm a professor at the University of California, San Francisco, and I'm using nanotechnology to develop an artificial pancreas. Imagine putting one capsule into the body and having it take care of diabetes for you. No more pinpricks, no more insulin injections, and it sits there for as long as that patient needs it. The pancreas does many things, but one of the most important functions is to regulate the levels of sugar in your body, and it does this by secreting insulin. What we do is we take the cells of the pancreas, the ones that secrete insulin, and we put them in this tiny capsule, which is nanoporous. So what that means is that they have little holes that are extremely small, and those holes allow for the insulin that is released by the cells to come out into the body, but they're small enough to keep out all of the things that might attack those cells. So this square device is actually a capsule, and it has a central reservoir where you can put millions of cells. And on the back of the reservoir,
first of its kind. These tiny little biohybrid swimming bots are capable of driving to viscous material through our bodies.
They take submersible nanomachines that can be controlled with UV light, and using the UV light, they can control where these nanomachines take nutrients and take medicines into the body.
As long as we have a way of controlling them from the outside, they can move around very, very quickly, perform a function. If we're looking at operating on a cancer, then potentially they could do that operation for you from within.
This could lead to huge advances in medicine, in healing, leading to nanomachines that could actually heal the wounds in our bodies, close things up much faster, repair damaged tissue, extend our lifespan, and literally bring us into a new level of human evolution.
Where'd that come from?
It's nanotech. You like it?